let's do this line here. How am I getting K? It's the slope of this line, okay? It's always got to be positive, so it's going to be the negative slope of this line, because the slope will be negative. I want it to be a positive value. But let's go ahead and do change in y over change in x, right? So I have 0 minus 1 sort of molar. I'm going to use this equation here, okay? I'm ending at 0 at a whopping 3.5 seconds. This is done reacting. And I had started at a 1 molar concentration of A. This is going to be equal to negative K times 3.5 seconds, okay? My final X minus my initial time point was always 0, T equals 0 for initial. Okay. Negative 1 molar divided by negative 3.5 seconds is going to give me K, which is equal to 0.28 molar per second. Okay. This is the direction of lower rate constants, okay? Slope is shallower. This is the direction of higher rate constants. The slope gets steeper. Okay. For a zero order reaction, concentration of product increases linearly with time. Concentration of your reactant versus T should be linear, okay? But what I'll tell you right now, I'm gonna go into the slides and we'll look at some slides, and maybe we'll take a break and then we'll integrate the first and second equations. But spoilers, first and second order aren't going to be linear. Okay. Any questions so far? Okay. So reaction rates. This is stuff I hopefully just wrote down for you, okay? But again, you can have either an instantaneous rate, you can have sort of a differential form, or if you actually have two time points that you're taking a difference between, then you have sort of a total difference in concentrations at those 2 time points, a total difference in time. These sort of capital deltas here for change in. Okay, we have our stoichiometric coefficients on the bottom. Okay, reaction rate is the change in concentration of a reactant or a product with respect to time. You can write it in relation to the concentration of any given reactant or product, whichever one you want. We like to write it in a way so that no matter which one we track, our overall reaction rate stays the same. Don't forget to put a negative sign for the disappearance of your reactants. Don't forget to put your stoichiometric coefficients in, okay, so that it won't matter. So again, this is just showing with time, A here is converting into B. Okay, A is our black molecules, B are the red ones. If you're given number of molecules, how do you get into moles? I have molecules and I want moles. Lauren. Divide by Avogadro's number. Great. How do I get into concentration once I have moles?
Divide by volume.
I'm going to have to divide by volume. So we don't have to be given a volume necessarily. But if you are just given molecules, you know how to get to moles. You'd also have to be given a volume so that you could get a concentration. Is this reaction zero order? And how do you know? So A is my reactant here, okay? Even though this is number of molecules here, I know that it's related to moles through a constant, Avogadro's number. The total volume I have isn't changing. This little square looks exactly the same. So my concentration, a volume isn't changing. Then my concentration is changing. I can think about it just in terms of moles changing or just in terms of molecules changing. And this drop off with time is not linear. So this is clearly not zero order. Okay. I only point this out to save yourself time when I show you some plot you haven't seen before. And rather than even bothering to try to do some math on any of the curves, just look at their shape and then you can answer a question very quickly. Okay. So to actually, like I said, to get this reaction order, you have to measure these things experimentally. So when we're at equilibrium, we know that the concentrations of reactants and products are constant, but it doesn't mean that reactions have stopped happening. It simply means that the rate at which we're making B and the rate at which we're making A, going back the other way, have reached an equilibrium so that the overall concentrations don't change with time. In order to observe kinetics and measure rates or rate constants, we would have to get away from equilibrium and then wait for equilibrium to arrive and take a bunch of measurements at different time points. So a rapid change in temperature or pressure would allow us to do this, and then you can wait for the system to relax back to equilibrium. Just one other option is some type of flow experiment, okay? So in this case, A and B are coming together to make something. You could keep them separated, and you could have some chamber where you essentially sort of treat it as soon as they meet. It's sort of a time point of 0. And then you could look at some change in signal. And we've talked about things like light spec or fluorescence or radioactivity or whatever it might be in order to actually sort of observe our change. And so in this particular example here, we have bromine, Br2. So this is sort of its molecular form that you'd expect to find it in, and it'll have a reddish-brown color. And as it reacts with formic acid, it separates. We just have protons, and we're going to have CO2, and everything is going to become, we'll have bromine ions, everything will become colorless. And so one of the things we've talked about many times is sort of this idea of using light spectroscopy or a change in absorbance to look at how the concentrations of things are changing with time. Okay. Bromine is going to absorb particular wavelengths of light, okay, based on this color. So if you hit it with some light, as the reaction is happening, you can get a change in concentration over time as it sort of goes from this sort of color change. And your change in the concentration of bromine will be proportional to the change that you see in your absorbance measurement. And like we said, the way to do sort of what is that change in absorbance, how does that relate to concentration, you'd have to set up a standard curve. So you'd have to have amounts of bromine from 0 to whatever, and you'd have to hit it with your light, read an absorbance measurement, and set up a standard. And now you know when you actually react it with something, how is it changing? This is the example from your book. And again, it just shows as a reaction was occurring, you could look at green fluorescence or absorbance and watch it drop off with time. Okay. And correlate that back to concentration change. Okay. Again, this reaction is not 0 order. Okay. I can tell as I look at the change in my reactant concentration. And I can measure instantaneous rates. So at 100 seconds, I have some sort of instantaneous rate of change. I can also look at 200 seconds, 300 seconds. So these are all sort of specific instant in time. Okay. Slope of the tangent line to the curve at a given point. Initial rate is instantaneous rate at t equals 0. Okay. This is often what chemists are usually interested in or are talking in very frequently. Okay. In this case, we have water reacting with chloral butane, maybe, I think. And we're making butanol and hydrochloric acid. Okay. And so again, instantaneous rate, initial rate, and average rate, you actually have to look at a difference between 2 time points. Average rate is going to decrease as the reaction proceeds because as you go forward, you have less and less reactant, so you have fewer and fewer collisions. So the reaction, in both the same with the instantaneous rate, you expect to be getting sort of slower and slower on this curve. The same will be true for your average rate, and you may see tables reported this way. Okay. Okay, so here is our generic form of the rate law. Okay, rate laws are always going to be written in terms of reactants exclusively. Okay. Like I said, we could write reaction rate in terms of the concentrations of products that are being formed if you want to. But for the rate laws, we'll only ever write them in terms of reactant concentration. Okay, and our reaction orders are our exponents here. So here's the example that I was trying to allude to. Fluorine and chlorine dioxide making chlorofluoride. Okay. So you're given this information here, and you're asked to figure out the overall reaction order. You're asked to figure out what is the reaction order with respect to fluorine and what is the reaction order with respect to your chlorine dioxide. Okay. So how would you go about doing this? Look at, like I said, we have to hold, first of all, the only way to do it is experimentally. So you have to be given experimental data or some plot or something, okay? There's no other way to get this answer. Okay. So in this case, I'm going to double the concentration of fluorine while I hold my chlorine dioxide constant. All right, so I said hold one of your reactants constant, vary the other, look at the difference in reaction rate. All right, so we have chlorine dioxide staying constant at 0.01. Fluorine, we're varying it, we're doubling it. And when we double it, what happens to this initial rate? It also doubles, okay? Going from 1.2 times 10 to the negative third molar per second to 2.4, okay? So if the rate doubles, as I double the concentration of fluorine, my exponent is just a 1, okay? How is the concentration change of fluorine affecting rate? It's a 1-to-1 change, okay? Fluorine doubles, rate doubles. Okay. Now I'll look at, okay, if I hold fluorine constant at 0.1 molar, and I vary the concentration of my chlorine dioxide, in this case I've quadrupled it, what happened to the rate? It also quadruples, so then how does rate change with concentration of chlorine dioxide? What does this exponent have to be? It also has to be 1, okay? So this was the example from last semester where we really freaked out about what was going on here with this 2 as a stoichiometric coefficient. But the reaction order for these things is 1. Okay, so notice we're also making 2 products here. So this is the stoichiometric coefficient. If I wanted to write reaction rate as sort of change in concentration of fluorine over time, it would be equal to 1/2 the formation of fluorine, I don't know what these are called, chlorofluoride. That sounds good. You know, if I want to relate this rate here to the rate of decrease of this, you know, it's twice as much. It's, you know, I need my stoichiometric coefficient here, but in terms of my rate law equation, there is no 2. And so reaction order, again, is coming from this idea that it has nothing to do with stoichiometric coefficient in a balanced equation. It has to do with how many of these 2 molecules would actually have to hit each other in order to make product. Easton.
So is that